Hi, welcome to our presentation, One Map Doesn't Fit All, Evaluating Saliency Map Explanation on Multi-Modal Medical Images. Our work evaluates the saliency map explanation with a focus on multi-modal medical images. I'm Weina Jing from Simon Fraser University. This is a collaborative work with Xiaoxiao Li and Gassan Hamarne. As computer scientists or engineers, when we deploy AI in clinical settings, we want AI to be able to explain their decisions to doctors. Explanation can facilitate doctors' trust and doctor-AI collaboration, as shown in previous studies. The saliency map is a common choice of explanation for medical images. It highlights important regions for AI prediction, as shown in previous works such as X-ray skin lesions. However, there is a problem when using saliency maps on multi-modal medical images. Those images are very common in biomedical field, such as MRI, PET-CT, pathological slices. The multi-modal medical images contain multiple images as the input, where each image modality or image channel represents different signals captured from the same underlying anatomical or physiological phenomenon. For example, doctors need to combine signals from T1 and T2 modalities from MRI to infer whether a lesion is actually a tumor, stroke, or infection. Those characteristics are distinct from natural images, for which the saliency map was originally proposed. Since doctors infer differently on multi-modal images, we don't know whether existing saliency maps can still fulfill the particular clinical requirements on multi-modal images. Therefore, we would like to propose these clinically motivated requirements to the technical community. The need for modality-specific explanation that is aligned with clinical prior knowledge, or simply multi-modal explanation. As a primary step towards this direction, in this work, we propose evaluation matrix and conduct experiments on existing saliency map methods regarding their multi-modal explanation property. We included 16 commonly used methods in the evaluation that covers the activation-based, gradient-based, and perturbation-based methods. The evaluation was conducted on a brain tumor classification task and 2 datasets. With the generated saliency maps, we first conducted a doctor-user study to seek doctors' clinical requirements and ratings on the saliency maps. And we found, given the task, doctors tend to prioritize the modalities. Therefore, we abstract such a notion into a computational metric called modality importance correlation. It measures the degree by which the saliency map correctly reflects the importance of each modality of the model. To determine the ground truth of modality prioritization, we use the Shapley value run on multiple modality ablation studies. We then calculate the correlation between the ground truth and modality-wise saliency map sum. Here are the results. For the ground truth modality importance identified by the Shapley value, they generally match with doctors' clinical knowledge, where the modality of T1 contrast enhancement is the most important, followed by the flare modality. The box plot shows the ranking with respect to the MI correlation. We can see that in general, many methods can correctly reflect the important modality for the model's decision, but with large variations on individual data points. As we dive into doctors' requirements, doctors expect the AI not only to reflect modality prioritization information, but also to correctly localize the discriminative features. The previous modality importance matrix is too coarse for such requirements. Therefore, we propose a second matrix that combines feature localization with modality importance, namely the modality-specific feature importance MSFI. MSFI contains 2 ground truth information, the modality importance ranking from the previous metric, and the feature localization mask or bounding boxes on each modality. The MSFI score measures how closely a saliency map to such a ground truth. So if a saliency map correctly localizes the important features for prediction, and also the saliency map values inside the feature mask agrees with such modality prioritization, the MSFI score will be high. Specifically, for each modality, MSFI calculates the portion of saliency map values inside the ground truth masks, weighted by the normalized modality importance value. We compare MSFI with doctors' ground truth rating, and there shows a moderate correlation. For the MSFI evaluation results, we conducted experiments on 2 datasets. One is BraTS dataset, which is from real patients, and the other is a synthetic dataset, where we have a better control of the ground truth. The box plot shows the ranking of saliency map methods with respect to the MSFI metric. MSFI is in the range from 0 to 1, the higher the better. We can see that MSFI scores for most methods are in the lower to the middle range. Even for the best performing method, their MSFIs have a very large variation among individual data points. This indicates most saliency map methods are not specified to fulfill the clinical requirements on feature localization as well as modality prioritization. This is a summarizing table of all the evaluation results. And here are some qualitative visualization for the best and worst performing methods. Based on MSFI metric, there are discrepancies between the current saliency map method and requirements for multi-modal medical image explanation. In summary, we propose the clinically motivated problem to the technical community, explain on multi-modal medical images. We also propose the evaluation metric MSFI and conducted experiments to evaluate saliency maps regarding their abilities to fulfill such clinical requirements.
MSFI could help to evaluate and select the saliency map method before their clinical deployment. Our evaluation also provides clinical insights for the proposal of new expandable AI methods, such as to incorporate clinical requirements on multi-module image explanation into the model training. Thank you very much for your attention.